What did galaxies in the early universe look like? The short answer is they are more chaotic than those in the nearby universe. For years, scientists strongly believed that the early universe was too chaotic in its early years, and frequent mergers would have disrupted galaxies' graceful shapes. But now, the widely held belief could be appended by James Webb. Immediately contrary to our existing understanding, the James Webb Space Telescope, or JWST, has just spotted thousands of Milky Way lookalikes that shouldn't exist, swarming across the early universe, flipping the entirety of our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. Join us today as we dig deep into how James Webb just rewrote what we thought we knew about the early universe. For 380,000 years after the Big Bang, the cosmos was a hot, dense mixture of protons, electrons, and other elementary particles and light elements. But the expanding universe was cooling fast, and once the temperature dropped to about 4,950 degrees Fahrenheit or 273 degrees Celsius, protons and electrons were able to form atoms. Not all atoms, mind you. No gold was floating around, or aluminum, or even elements as light as oxygen. Hydrogen, in its heavy isotope deuterium, accounted for about 3/4 of everything. A couple of isotopes of helium accounted for most of the other quarter, and a tiny fraction, about 1/1000th of everything, of lithium had also been produced. Just because brand new hydrogen and helium were swirling around doesn't mean stars were popping into existence. In fact, the first of those luminous objects didn't appear until the universe was about 100 million years old. So, for a span of time longer than the dinosaurs have been extinct on Earth, there were no stars or galaxies, or for that matter, any object emitting light. It's out of this darkness that astronomers are trying to piece together the origin of the first generation of stars, called population 3 stars. As brightly as they shone, their light is now too faint to be detected by current observatories, and even the next generation of telescopes will struggle to spot them. But through scientific detective work, astronomers are beginning to understand how these elusive objects lived and died. A major clue comes courtesy of the cosmic microwave background, or CMB, the relic radiation that formed in the hot early universe. This radiation has been cooling ever since it was emitted as the cosmos expands. Currently, the background temperature is about 2.73 K or -45 degrees Fahrenheit or -270 degrees Celsius, and measurements of the CMB show that it is incredibly consistent, corresponding to density variations of only 1 part in 100,000. But those variations, literal ripples in the structure of the universe, are revealing how the first stars formed. Computer models show that the minuscule density fluctuations in the early universe acted as starting points for immense clouds of gas. Without these variations in structure, nothing would have formed, and the whole cosmos would have evolved into an ever-thinning, homogeneous cloud of hydrogen, helium, and that tiny bit of lithium. Thanks to gravity, however, the fluctuations became gathering points, huge clouds where gas continued to collect. Eventually, the clouds contracted, and as they did, they heated up to more than 1,300 degrees Fahrenheit or 700 degrees Celsius. That temperature would be far too high for a star-forming region today to form stars. Indeed, if a cloud is hotter than about 10 Kelvin, the speed of the atoms inside it will be too fast for them to stick together and eventually form stars. But the clouds in the early universe were larger and much more densely packed than modern-day nebulae. Within them, some hydrogen atoms paired up to become hydrogen molecules. And because molecules are better emitters of infrared radiation or heat, the temperature dropped, and clumps inside the clouds could contract further. Each of the regions was probably several hundred times as massive as the Sun. That much mass and its corresponding gravity could overcome the outward pressure from radiation. The clumps didn't split as they contracted, so only a single star formed from each one. The result was that the first stars were potentially colossal. Estimates range from several tens of solar masses up to 1,000 solar masses and luminous, perhaps millions of times as bright as the Sun. Because the universe was smaller and denser, vast numbers of these stars formed near each of its density variations. Eventually, the gravitational pull from these stars would attract other stars, and the numbers grew from there. Astronomers think this took a few 100 million years, but at the end of that time, the first galaxies had formed. However, early galaxies were not like those we know today. The first galaxies were more pristine, composed primarily of hydrogen and helium gas. Over time, their stars would fuse atoms to form heavier elements. And when these stars died in supernova explosions, the heavy elements dispersed throughout the galaxies, enriching them with star stuff, including the elements needed to create life. The first galaxies had yet to settle into majestic spiral patterns or puffy elliptical balls like the galaxies we see around us today. They were far more disordered and much smaller, making them even harder to find. The earliest galaxies we have seen were about 1% the size of our Milky Way, but they were growing rapidly, forming new stars at prodigious rates. Fuel was plentiful back then. Early galaxies were bathed in cool streams of flowing hydrogen gas, lured inward by gravity. The galaxies collided with one another emerged frequently, accelerating their growth and triggering new bursts of star formation. As the universe expanded over time, gas galaxy growth slowed, significant mergers became less frequent, and the gas supply thinned out. This picture is our basic understanding of cosmic history. We are still working to fill in the details, and many questions remain, especially surrounding the earliest times. When did the first galaxies form? How small were they? What did they look like? Were they building blocks of galaxies to come with single large regions of star formation, or were they more fragmented and clumpy? Were they all bursting with intense star formation, or were some more relaxed like most galaxies today? Did any early galaxies have time to settle into disks like the Milky Way did? Or were they merging too frequently to do so? Will we ever find any filled with pristine hydrogen and helium gas? Or did the first supernova enrich them too quickly with heavier elements? How rapidly did the early galaxies build up in mass and numbers? And were they, in fact, responsible for reionizing the early universe? So many questions. But now, with James Webb, we will take another step toward answering these questions. The first step toward answering the first chapters of the universe is finding and confirming the distances to galaxies that astronomers think might be responsible for this process. Since light travels at finite speed, it takes time to arrive at our telescopes. So astronomers see objects as they were in the past. For example, light from the center of our galaxy, the Milky Way, takes about 27,000 years to reach us on Earth. So we see it as it was 27,000 years in the past. That means that if we want to see back to the very first instance after the Big Bang when the universe is 13.8 billion years old, we have to look for objects at extreme distances. Because galaxies residing in this time period are so far away, they appear extremely faint and small to our telescopes and emit most of their light in the infrared. This means astronomers need powerful infrared telescopes like the James Webb Space Telescope to find them. Prior to Webb, virtually all of the distant galaxies found by astronomers were exceptionally bright and large, simply because our telescopes weren't sensitive enough to see the faint or smaller galaxies. However, it's the latter population that is far more numerous, representative, and likely to be the main drivers of the reionization process, not the bright ones. So, these faint galaxies are the ones astronomers need to study in greater detail. It's like trying to understand the evolution of humans by studying entire populations rather than a few very tall people. By allowing us to see faint galaxies, Webb is opening a new window into studying the early universe. And in a recent unimaginable observation, the supreme time machine, the James Webb Space Telescope, once again shocked the whole world, as it detected more than 1,000 galaxies mysteriously resembling our own Milky Way, hiding out in the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgängers were found by the James Webb Space Telescope more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. Yet, the disk galaxies are 10 times more common in the early universe than astronomers previously thought, new research reveals. The strange discovery joins others made by the JWST that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. The researchers published their findings in the Astrophysical Journal. According to lead study author Leonardo Ferreira, an astronomer at the University of Victoria in British Columbia, Canada. For over 30 years, it was thought that these disk galaxies were rare in the early universe due to the common violent encounters that galaxies undergo. The fact that JWST finds so many is another sign of the power of this instrument, and that the structures of galaxies form earlier in the universe, much earlier in fact than anyone had anticipated. Most theories of galaxy formation began 1 to 2 billion years into the universe's life, by which time the earliest clusters of stars were thought to have morphed into dwarf galaxies. These dwarf galaxies subsequently began cannibalizing each other, sparking a free-for-all of violent galactic merges that, after 10 billion years, resulted in large galaxies like our own. The Milky Way is a disk galaxy, with its spiral arms and squash sombrero shape. It is one of the most common types of galaxy in today's universe. However, during the universe's early years, when the cosmos was more cramped and dwarf galaxies swarmed, astronomers long assumed that galaxies like our own would be quickly twisted out of shape. Yet, by using the JWST to peer from 9 billion up to 13 billion years into the past, the astronomers discovered that out of the 3,956 galaxies that they had spotted, 1,672 were disk galaxies like our own. Many of these galaxies existed when the universe was just a few billion years old. A study co-author, Christopher Consolis, a professor of extragalactic astronomy at the University of Manchester, said in a statement, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. These new JWST results pushed the time these Milky Way-like galaxies formed to almost the beginning of the universe. This implies that most stars exist and form within these galaxies, which is changing our complete understanding of how galaxy formation occurs. Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. Our own existence in a disk galaxy means that astronomers usually assume they must have good conditions for sparking life. Well, if that's the case, it's possible that life could have started earlier in the universe than first thought. Put early galaxies aside. New remarkable findings from the JWST have just shown that efforts to observe the atmospheres of planets in the TRAPPIST-1 system are being stymied by rambunctious activity on the surface of the red dwarf star at its center. In March 2023, the JWST's mid-infrared instrument, or MIRI, observed the secondary transit of one of the TRAPPIST-1 planets, known as TRAPPIST-1b. The observatory found that the planet, which is the innermost world of this system and a little more massive than Earth, is probably a bare rock with no atmosphere to speak of and a surface temperature of 232 degrees Celsius 450 degrees Fahrenheit. Similar results came from the next planet in this system, TRAPPIST-1c, 3 months later. These two worlds seem analogous to Mercury, which is the innermost planet of our solar system. And new observations from a team of astronomers led by Olivia Lim of the University of Montreal corroborated these earlier findings by taking the first-ever spectrum of a planet in the TRAPPIST-1 system, specifically TRAPPIST-1b. While a thin atmosphere cannot yet be ruled out on TRAPPIST-1b, the spectrum captured by JWST's near-infrared imager and slitless spectrograph, NIRIS, shows no evidence for a thick hydrogen-dominated atmosphere. However, there is one interesting caveat to these findings. What we do see is that the star is absolutely the biggest effect dominating our observations, and this will do the same thing to other planets in the system, said team member Ryan McDonald of the University of Michigan in a statement. Or in other words, that tumultuous red dwarf might be preventing scientists from learning the truth about whether TRAPPIST-1 can be considered habitable or not. To take a spectrum of an exoplanet's atmosphere requires the use of a method known as transmission spectroscopy. When a planet transits between its star and our vantage point on Earth, much of the starlight is blocked by the planet itself. But some of that light also shines through the planet's atmosphere, if it has one. And those rays that go through the atmosphere also get absorbed by molecules in the atmosphere at characteristic wavelengths. And if that light hits our Earth-based detectors, scientists can then look for the absorption lines in a planet spectrum to discern what gases are present in the world's atmosphere. But the problem is that the red dwarf stars like TRAPPIST-1 are typically very active stars with bright flares and large dark star spots. These feisty events interfere with measurements of a planet's spectrum, creating contrasting bright lines and dark lines that can mimic absorption lines. In addition to the contamination from stellar spots and flares, we saw a stellar flare, an unpredictable event during which the star looks brighter for several minutes to hours, said Lim. This flare affected our measurement of the amount of light blocked by the planet. There are ways to mitigate this, though. One solution is to try and model what the stellar activity on the surface of TRAPPIST-1 is like and then remove it from the data before analysis. The other is to model the stellar contamination and the planet's atmosphere together and fit them to various models of what the planet's spectrum might look like depending on different kinds of atmospheres. Lim's team took both approaches and came up with the same result both times. TRAPPIST-1b lacks a thick hydrogen atmosphere, and its spectrum can be fully described by the star's activity. This is not surprising. Of all 7 planets in the TRAPPIST-1 system, Planet B is the most likely not to have an atmosphere because it feels the full brunt of the star's stellar wind and violent flares that can blow an atmosphere away. However, it's impossible to say whether the planet has a thinner atmosphere of water vapor, carbon dioxide, or methane, as the uncertainty incurred by the star's activity is an order of magnitude greater than the precision required to detect such an atmosphere. This will pose serious problems for observing the spectrum of the other worlds in the system. If we don't figure out how to deal with the star now, it's going to make it much harder when we look at the planets in the habitable zone, TRAPPIST-1d, E, and F, to see any atmospheric signals, says McDonald. In another effort to unlock the secrets of the universe, photos snapped by the James Webb Space Telescope have revealed the farthest ever example of an Einstein ring. The record-breaking halo of warped light, which is a whopping 21 billion light-years away, is unusually perfect and surrounds a mysterious dense galaxy. An Einstein ring is an extremely rare type of gravitationally lensed object that was first predicted by Albert Einstein's theory of relativity. Gravitational lensing occurs when the immense gravity of a massive foreground object, such as a galaxy cluster or a black hole, warps spacetime around itself. Light emitted by more distant objects, such as galaxies or supernovas, that passes through this warped spacetime also appears curved and warped from our perspective on Earth. This effect also magnifies the light of the object being lensed, similar to how a magnifying glass works, allowing astronomers to study distant objects in greater detail than is normally possible. Most gravitationally lensed objects form arcs or partial rings that surround the foreground object. But a true Einstein ring forms a complete circle around the closer entity, which is possible only when the distant object, foreground object, and observer are perfectly aligned. In a new study uploaded September 14 to the preprint server AR14 and accepted for publication in the journal Nature Astronomy, researchers discovered the new nearly circular Einstein ring, named JWST R1, within the Cosmic Web Survey, a detailed map of more than 500,000 galaxies captured during a 200-hour continuous JWST observation. JWST R1 has 2 parts. JWST R1G, the compact galaxy that acts as the lensing object in the foreground, and JWST R1R, the light from a more distant galaxy that forms the luminous ring. JWST R1G is located around 17 billion light-years from Earth, while JWST R1R is another 4 billion light-years farther away. Until now, the farthest detected lensing object was around 14.7 billion light-years away. According to BigThink.com, while the age of the universe itself is estimated to be around 13.7 billion years, the universe's constant expansion means that light from the oldest objects must travel much farther than this to reach our telescopes. Thanks to the complete ring of JWST R1, researchers calculated the mass of the lensing galaxy by seeing how much it had warped spacetime around itself. This revealed that the galaxy has a mass equivalent to around 650 billion suns, which makes it unusually dense for its size. Some of this extra mass can be explained by dark matter, the mysterious invisible matter that makes up around 85% of all matter in the universe. But even then, it is unlikely that there are enough stars to account for the rest of the galaxy's heft. Based on the researchers' calculations, additional mass is needed to explain the lensing results, but it is not exactly clear what this mass is. Other similarly odd and equally dense galaxies have been detected before, which suggests that there is something common about these ancient star factories that makes them so massive, the researchers wrote in the paper. One explanation is that these galaxies harbor much more dark matter than expected, while another theory suggests that they may have more small-mass stars lurking within them than younger galaxies do. But more work is needed to find out. This is not the first true Einstein ring spotted by the James Webb Space Telescope. In September 2022, a Reddit user discovered a perfectly circular ring of light from the galaxy J043947.08, plus 163415.7, located around 12 billion light-years from Earth, lensed around a closer galaxy. The observatory has also utilized gravitational lensing to snap the most distant star ever detected and one of the universe's oldest galaxies. The James Webb Space Telescope has been designed to answer many of the core questions that have animated astronomers over the past half-century. And with a $10 billion price tag, it is one of the most ambitious engineering initiatives ever attempted. But now, you see, it is completely worth every penny. The most powerful observatory now is enabling cosmologists to write ancient history, not the history of the Greeks and Romans who lived a mere blink ago. Rather, it is the history of our universe, the history of everything. We know that we are made of star stuff, linking our origins to the rest of everything that exists in the universe. Thus, to know the cosmic history is, in a very real sense, to know our own. As we trace our material origins to the cosmos, we bridge our existence, our individual and collective history, to the universe at large. Our predecessors looked up at the skies, trying to make sense of powers well beyond their reach. And despite the challenges and complexity, we never gave up trying to understand. That we can now tell large parts of the story, linking the very early times after the Big Bang to our own existence, is nothing short of wonderful. We owe our deepest gratitude to the scientists and engineers responsible for the design of the James Webb Space Telescope and its successful deployment. Our temples now float in space, their eyes trained at the distant stars.